Welcome back. This is part 2 in your series of gas lectures. Hopefully you got a lot out of the first series and the first lecture, and let's just kind of continue that theme as we go on here. Now, I know it's kind of hidden at the top, but there's something that this is called the combined gas law. And this is really going to be imperative that you understand how to do this in terms of manipulating it, moving it around, and knowing how to get from one set of laws and one set of conditions and one set of gases to a totally set of separate conditions. Basically, what they're going to do is they're going to flip the experiment on you. They're going to say you're going to start with this certain kind of conditions, and then we're going to manipulate those conditions, and then what would the outcome of one of the variables be? And so you're going to be able to need to do basic algebra skills in order to do this. All right? So what is going to be relating are the three main variables of any kind of gas calculation or any kind of gas issue that we have. The three variables are pressure, volume, and temperature. And so from the last lecture that you saw, we know that pressure is based on collisions. You know that if you decrease the volume, you increase the pressure. You know that temperature, heat them up, speed them up, increases your pressure. So all these variables are interchangeable. So this is a combined gas law. Now, it's actually written twice, and again, it's kind of funky the way that it is done in the slide here. So let me just kind of draw a line. These are the two ways to do it. Now, I'm going to be honest. If I have my preferential way, I would completely ignore the top one. And the reason why is because it makes it a little bit harder for you to move around algebraically. And the way that I've taught this is that if you do it P1 V1 T2 equals P2 V2 T1, it is very simple. And the way that you can remember how to do it is you remember the tricky T's. They're trying to mess you up with the T's. And the T's will actually go in its opposite effect, okay? So let's just hypothetically say, all right, here's the, you have this gas, it's at this pressure, at this volume, at this temperature, and all of a sudden we've changed the temperature to this, and here is the new volume, and we've condensed the volume. What's the new pressure? Well, guess what? They've given you your original pressure, they've given you your original volume and your original temperature. They tell you they changed the temperature to something else, and then they compress the volume, and then you need your new pressure. Well, this should be a very simple calculation. It's just a basic arithmetic algebra move around. So P2, basically what you're going to do is divide each side by V2 and T1. So you get P1, V1, remember tricky T's, T2, over V2, T1. Well, you take your numbers they gave you, plug them in, and go from there. So again, it makes it a little bit easier in terms of algebraically moving things around. So please just, what I would recommend is I would definitely recommend this bottom one. It makes life a whole lot easier if you'll just do it that way. All right. So that's the combined gas law. And the way the combined gas law was formed was from three other separate laws. All right. We're going to go through those three other separate laws. I'm going to be honest with you, I've never seen these laws asked for explicitly, so I'm going to kind of run through this real quick and just talk about the bare minimum. Boyle's law, the way I have an easy way to remember this is that the temperature is held constant, all right? Remember, temperature is held constant. That is the key here. Highlight that. Know that. Boyle's law, temperature is held constant. And again, the way I kind of like think about it, if you're boiling water, the way you would essentially boil water is you turn the heat all the way up on the stove, you keep the heat constant, and it's going to sit there and boil, all right? So basically, this is the exact same, apologies, again, I keep messing this up. I got to figure out how to stop doing that. This is the exact same law as the combined gas law, except what's missing. We'll go back to the previous slide and look. From the previous slide, the only thing that's missing is your T's. Well, why are the T's missing? Well, of course, because if you're thinking logically, it's because the T's are being held constant. So that's why. So Boyle's law has been tested for over 3 centuries, and it holds true. But notice what it says. Very, very, very important. It only holds true at low pressures. All right, so look at what happened. Let's look at the graph. Pressures versus volume. As your volume increases, notice what starts to happen to your pressure. Hopefully you recognize that relationship. So this is what I need you to get. As your volume goes up, what happens to your pressure? Your pressure goes down. So how are these two things related? This is what I would get out of this. They are indirectly related. So as one goes up, the other one must go down. Very, very, very important. So Boyle's law, pressure, volume, indirectly related, okay? Here's another little thing. I do want you to kind of know this. I think you can see this on your notes, but this blue dotted line that runs right here, that arrow, what it says is that dotted line is your ideal gases. This is kind of interesting. Notice where it's located. It's at the 22.4 range. Remember we talked about ideal gases? We like for them to be 22.4 in terms of at 1 ATM. So a plot of PV versus P for several gases at 1 ATM, picture to the left. So notice how these gases deviate. As your pressure is increased, notice what happens to the PV constant. They almost all start going down except for neon, and again, and we'll kind of adjust for that. So why do the gases deviate from ideal? Well, they're not ideal. They have the intermolecular forces. They have unelastic collisions. They have these things. So again, to go back, and what I would recommend doing is go back and look at the previous slide where we talk about the kinetic molecular theory and ideal gases. So an ideal gas is expected to have a constant value of PV shown by the dotted line. And again, that's an ideal gas. CO2 shows the largest change in PV, which is this huge, large drop. But notice something. But it's actually quite small, because if you look at your PV value, it goes from about 2.41 down to about, 22.2627. So it doesn't drop a whole lot, but it still does drop, okay? So you're going from 22.39 is what it's, I don't want to say that, so it's actually 22.41, that's actually a typo, to about 22.26, all over a large change. Oh, okay, I see what it says, from 0.25. So you're looking at about right here is what it's talking about. So with that kind of a change, it's only dropping that far. So Boyle's law is a good approximation at relatively low pressures. And again, less than 1 atmosphere. All right. Again, here's some more videos. I would really recommend you pausing the video, look them up. Really cool. I don't have one Easter Peep. I couldn't find that, but Pierre and Marie Learn About a Vacuum. Really cool video. I would encourage you to look it up. Okay. All right, so here's one of our first problems. We have sulfur dioxide, a gas that plays a central role in the formation of acid rain, is found in the exhaust of automobiles and power plants. Okay, interesting. Consider a 1.53 liter sample. All right, well, excuse me. What that just told me is that is a volume. All right, so we have a volume of gaseous SO2 at a pressure of, all right, well, there's our P. If the pressure is changed, all right, so now they're altering our variables. So what we can do is we can say that's our first pressure and that's our first volume. So the pressure is changed to this temperature, and then it gave us something really important. At a constant temperature. So as soon as they tell you that, you need to assume that Boyle's law is in effect. Boyle's law is in effect. So what is Boyle's law? It is P1 V1 equals P2 V2. And again, where are your T's? Remember, the tricky T's aren't involved here because the temperature is constant. What will the new volume of the gas be? New volume. So we're going to be solving for V2 here. All right, so let's algebraically rearrange. So V2 equals P1 V1 over P2. Well, now it just turns into a plug-and-chug equation, guys. So you can just take your numbers and plug them in. I'm not going to plug numbers in just because I don't want to fit it in, but I do encourage you to plug in your numbers and calculate it up. And the answer that you should get, please, I do encourage you to try this. Make sure you get the right answer, is 0.57 liters. Okay, this is your V2. That is your V2 that you need to keep in mind of what's going on there, okay? So that's your first Boyle's Law problem. Again, moving on through these kind of quick. This is it's kind of one of those weird things. I don't really understand the whole logic behind it, but I can explain it. For a given quantity of gas, notice what that said. For a given quantity, above quantity, please do me a favor. Please write the letter N, and N is your number of moles. So basically, your number of your quantity is going to be defined at a constant temperature. As soon as you see constant temperature, what's that law? boils, the product. Now what does product mean? That means times. It means you're multiplying. Pressure times volume is a constant. Notice what it just said. So for a given quantity, which means I know for a specific amount, if it's at a constant temperature, the pressure times volume should be a constant. So P times V, should equal K. Well, let's look at this. If you rearrange for V, we have K divided by P. We are almost equating that to be 1. All right. Well, what is the slope of a line if it's a constant? Well, anywhere you take the slope of a line, it should be the exact same no matter where you take it. So which is the equation for a straight line? So let's look at this next little part we have going on, and it's this right here. In the study to see how closely the gaseous ammonia obeys Boyle's law. Let's talk about that. Boyle's law, what's held constant? Excuse me, my apologies. Boyle's law, what's held constant? Hopefully you say T is constant. Several volume measurements were made at various pressures. Notice what it said. Several volume measurements at various pressures using 1 mole. Guess what they just did? They just quantified your gas. They just told you it's this much. It's not going to be any different from that. At a temperature of 0 degrees Celsius. Well, guess what else they just did? They just told you it was at STP. Okay? Using the results listed below, calculate the Boyle's law constant. Well, I just gave you that formula. P times V equals K. P times V equals K. So this is what I want you to do. I want you to go ahead and calculate all of these. I will give you the first one. All right. So 0.13 times 172.1 is going to give you a rough estimate of about 22, let's say, 0.4. That number looks pretty familiar if you ask me. So what I want you to do is just go ahead and calculate all of these values and see what you come up with and see if you can determine what the significance of that is. Okay, see if you can go ahead and do that. There is one thing that I do want to mention. Notice what's happening. What is happening as your volume, and again, this is part of the significance, but I want you to grasp that. As your volume decreases, again, it's getting smaller and smaller and smaller. What is happening to your pressure? You said it's increasing. That is very good relationship skills. So again, as your volume goes down, what is happening to your pressure? It's increasing. So we've already defined this earlier. The volume and pressure are inversely related. Okay, that's the concept there. All right. Charles's law, the next one. The way I kind of teach this concept is think about Charles as a person. Charles may be your teacher, but Charles is the guy that will keep the pressure down on you. He's going to make you work hard. He's going to make you do what you got to do at all times. So again, Charles is the pressure guy. So in Charles's law, your pressure is going to be held constant. Well, guess what happens? That throws your tricky T's back into play. If you like divisional problems, you can use that. I'm fully okay with that. However, again, I don't recommend it. I recommend your V1 T2 equals V2 T1. Again, it's your tricky T's. They're playing with you here, okay? Well, let's talk about it. You need to know that your volume is directly proportional to your temperature. Well, think about that. We know that if you heat them up, you speed them up. Well, let's think about a balloon. You take a balloon, you start heating that balloon up. Think about a hot air balloon. Okay, we're just going to start on the ground. Okay, we're going to start on the hot air on the ground in a basket, and we have this kind of deflated hot air balloon. Well, how do you get the hot air balloon to rise? What are you going to do? You're going to add a bunch of heat. Well, as that temperature increases, what is going to happen to the volume of the balloon? Well, guess what? It starts filling up. So that is the concept that you need to understand. As that the higher the temperature goes, the more your volume will increase. All right? So those things are directly related. Okay? All right? So let's go from there. Now, why is Kelvin used? And again, I think the part that I just missed there that I need to go back and look at is that, remember, your temperatures must always be in Kelvin. That's probably one of the biggest things you need to highlight, that you can never use a Celsius temperature here, okay? Please make sure you grasp that. So why are we going to use a Kelvin temperature. Really important to grasp. All right, so let's look at it. This figure shows the plot of V versus T. Now again, volume versus temperature. So if you'll notice, your volume is right here, and your temperature is down here. So as your volume gets larger, and as your temperature increases, you can see the relationship. You can see it's getting larger. So as your temperature starts to get higher and higher and higher, the volume gets larger. Now, every gas will expand at a different ratio, and we're going to get into why that's true. But it's obvious that as the higher the temperature goes, the larger the volume is going to get. This is something you do need to read, though. The solid lines represent experimental measurements on gases, okay? The solid lines. And you can see right here that there are a few situations, again, we changed the color so you can see it, that there are a few situations where there are some dotted lines represented. Well, a dashed line represents an extrapolation. Now, the first thing you need to understand is what is extrapolation. Basically, it's a guess based on calculations. They sit down, they run all these calculations through different things, and they determine, well, this is what we think it would be. Okay, we think it would be. Of data into regions where these gases would become liquids or solids. Now, why in the world would a gas that's running 1,000,000 miles an hour all of a sudden turn into a liquid or a solid? Well, I need you to notice something. Look at this temperature. Right here is 0, and look at what it is. It's in Celsius. So we know that water, which is right here, will freeze at Celsius. So notice what it's coming to. At 100, water does what? Well, hopefully you say water boils at 100 and then freezes. So from this dotted line back, we know that it's in its liquid and its solid stages, because beyond 100, it's in a gas stage. Okay? Because it boils at that point. But anything less than 100, we know it's going to be a liquid. Anything less than 0, we know it's going to be a solid, okay? Because we know it freezes at that. So note that the samples of the various gases contain different number of moles. Excuse me, that is in fact an invalid state. Okay, let's cross that off. My apologies, that needs to be taken out. So what is the temperature when the volume extrapolates to 0? So notice, the key there is that every single gas, no matter the gas, all hit this point where they all have a volume of 0. Well, this is the point right here, negative 273 degrees Celsius. Well, if we need Kelvin, we know that if we need it, we add 273. So negative 273 plus 273, well, that's obviously Kelvin is going to be 0. Well, what is the term called when Kelvin is at 0? This point is going to be absolute 0. And again, I would write this below this. What do we know about absolute 0? That all motion ceases to exist. So the reason we use Kelvin is because it allows us to calculate things easier, and we know that when it hits 0, it's done. That's it. There's no more calculations you can do. There's no more volume. There's no more pressure. That's it. All right? So that's why we do use Kelvin. All right. So here's our first Charles Law problem. A sample of gas at 15 degrees C. Uh-oh, that's an issue. We need to get rid of that. So we need to change that to what? Because all temperatures must always be in what unit? Hopefully you said that is supposed to be in Kelvin. That is 288 Kelvin. All right, and we know that is a T. At 1 atm, well, there's our pressure, has a volume of that. All right, so then it gives us a V. So hold on, they give us a T, a P, and a V. We need to keep reading. What volume will this gas occupy? Well, there's our question. We know we're going to need a volume. So we can go back and we can relabel this as V1, T1, and P1. And we're going to be solving for V2. Will this gas occupy, let's get rid of that, change that to Celsius. That's going to be 311 Kelvin. Change it from Celsius to Kelvin. I have a kind of a phrase here. If you see a C, change it to a K. If you see a C, change it to a K. And then notice something. This is really imperative that you get. Because I can see how you would say, oh, it gives you a P, a V, and a T. and they give you the exact same on the bottom. Well, this is just a combined gas law. That's all you would need. Just do it that way. But the thing that I want you to grasp and notice what your pressure is. 1 atm and 1 atm. So essentially, your pressures have zero effect on this calculation because your pressures are constant. Well, whose law is that? Again, that's Charles's law. So your P is constant, so we don't need that. All right, so again, we're at Charles's law, and please remember your tricky T's here. All right, so the formula is V1T2 equals V2T1, and we're solving for V2. So algebraically, you can set it up. V2 equals V1T2 over, sorry, I forgot my one there, over T1. And again, you can label all your variables. You can plug them in. Again, please, on test day, please plug in the numbers and show them what you're doing here. I don't have the space nor the time to do it. And double check, make sure you get this answer. The answer I got was 2.79 liters. Okay, 2.79 liters. And double check, make sure that that is the correct answer that you got as well. All right, here's another YouTube video, the MIT physics demo, balloons and liquid nitrogen. Really cool. I encourage you to check it out. All right, the final one, Gay-Lussac. So we've talked about pressure being constant. We've talked about temperature being constant. Well, the last variable that we have to remain constant is volume. That's Gay-Lussac. I don't have an easy way to remember this one being constant, but volume is your constant here. All right, and another way that I need you to grasp and recognize is the fact that your temperature and pressure are directly related. So essentially what I need you to know is that as your temperature, let's change this back to this. All right, as your T increases, well, guess what your P does? Your P also increases. And this is where your heat 'em up, speed 'em up things come from. The higher the temperature, the faster they go, the more the collisions, the higher the pressure is going to be. And again, I teach this with encouragement of don't use this one. Use the tricky T model. It's a little bit easier to do in terms of being able to figure out what's going on down here. Okay, use the tricky T model. I do not have a question here again, but just make sure you know that Gay-Lussac is constant. All right, we're a few minutes into this video. I do want to cover about, let's see, 1, 2, 3, 4, 5, 6 more slides, and we'll call it quits on this video, make it a little bit shorter. Guys, I cannot stress to you how important that this law right here is. I really can't. I don't know where to begin with it in trying to get across to you that Avogadro's law is very important because they are very sneaky in how they ask you about this question, and you don't recognize or realize they're talking about Avogadro's law until it's too late or you don't recognize it at all. All right? And again, I've already put right here, this is one of the most important laws of all. Okay, so here's what it was. This is Avogadro's hypothesis. Yes, this is the same guy as the number, 6.02 times 10 to the 23rd. This is where all this came from. This is his hypothesis. Let's read it very carefully. Equal volumes. All right, equal volumes, which means the container looks the same. Equal volumes of gases under the same conditions of temperature and pressure. So essentially what I'm telling you, my apologies. I promise I'm going to stop doing that eventually. This equal volumes of gases under the same temperature pressure. So basically I have created this environment that they're sitting in the same room and I have trapped them under the same conditions of pressure. Here's the biggest key. Equal volumes, same temperature and pressure, contain equal numbers of molecules. I cannot stress to you how important this concept is. So if you have the same temperature, the same pressure, the same volume, it must have the same number of molecules. It does not matter what gas it is. It can be helium, hydrogen, nitrogen, carbon dioxide, oxygen. You can throw out 1 billion different gas molecules. But if they have equal volumes, same temperature and pressure, they have the same number of molecules present. All right, so what does that mean for us? What that means is the volume of a gas at a given temperature and pressure is directly related to the quantity of gas. So the volume and the quantity are directly related. So what does that mean? The more molecules we have, the more collisions we have, the more pressure we have. That's essentially what we're kind of getting into. So let's look at this example right here. These 4 balloons, we have nitrogen in one, we have hydrogen in one, we have methane in one, and we have argon in one. These are obviously all 4 different gases. However, if I tell you that the volume of that balloon is identical, it's under the exact same pressure in the exact same room at the exact same temperature, every single one of these balloons will have the exact same number of molecules. One more time. These balloons will have the exact same number of molecules. Now, if you want to read into it over here, these balloons hold 1 liter at 25 Celsius. Now, we know that's not good for us. So let's go ahead and change that to 298 Kelvin. And 1 atm, each balloon contains 0.041 moles of a gas, or if you want to go any further, 2.5 times 10 to the 22nd molecules. Now, I know what you're thinking. What in the world is this random number right here? Where did that come from? The next video that you're going to get is going to talk about the ideal gas law, which hopefully you know as PivNerd. So what are we saying here? Well, essentially what we're trying to do is solve for the number of moles. So we're trying to solve for N, which is PV over RT. Now, I'm going to talk about this in the next video, but it tells you explicitly the pressure is 1 atm. It tells you explicitly the volume is 1 liter, and then we also correct it for the temperature. So we have 1 atm times 1 liter. Now R, we're going to talk about that next video, and times 298 K. So what I'm essentially telling you is that when you plug R in, you're going to get 0.041 moles. Okay, and again, that is a constant. That is what's and any time you have 1 atm, 1 liter at 290, and this is 298, sorry, and then R. Again, R is a constant. We'll cover next time. You're going to get 0.041 moles. And this is any gas. I don't care what gas you ask me about. That is the part that people mess up. Any gas. Doesn't matter. That is Avogadro's hypothesis. That is his law. Extremely, extremely, extremely important. Okay? All right, so suppose we have a 12.2 liter sample. Let me go back. A 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atm. All right, so far, guess what they've given us? They have given us a V, they've given us an N, and they've given us a P, and a temperature of T. Now, again, we know that's going to be 298 K. We don't like Celsius, so we have 298 K right here. Plug that in. If all of this O2 were converted to ozone at the same temperature and pressure, what would the volume of ozone be? Notice, they've given you a clue. They've given you a huge clue. At the same temperature and pressure, you're going to have the same content value there. But here's the only problem. We're actually converting. And we know that oxygen and O3 are the same thing. So really, if you want to break it down, we're doing this right here. We're going from O2 to O3. And someone should be yelling and screaming, hey, that's not balanced. You're right. It's not balanced. Okay? So remember, this is your 2-3-6 rule. So put a 2 here, put a 3 here. Now they're both balanced. So, but remember, since it is under the same temperature and pressure, it is going to contain the exact same number of moles. But it's not asking about moles. It's asking about the volume. All right? So the volume has to be altered based on the number of, or based on the change in the mole ratio. So we have 12.2 liters, okay? And basically, it's just a mole-to-mole conversion. So we're going from 12.2 liters of O2, sorry, I should have plugged it in, to 3 liters of O2 to 2 liters of O3 is your stoichiometric conversion. Just think about it. Just stare at it long enough. Again, the moles will stay the same. That's not going to change. Your volume will change because it is a different molecule. They're going to create a different, the molecules are going to hit at different velocities, they're going to hit at different forces. So again, we've got to change that. But they're going to have the same amount of energy. So 12.2 times 2 divided by 3 brings you out to 8.1 liters. All right, so notice what happens. We have 3 moles of O2. It decreased to 2 moles of O3. And what happened to the volume? The volume got less, even though there were the exact same number of molecules, your temperature and your pressure were the same. Okay, so what does that tell you? That basically the less number of moles you have, you're going to have a smaller volume. Okay? All right, so let's go from there. And here's an easy way to remember all this. And again, I kind of have a few of the things out of order, but I do want to kind of show you this. Is P1V1T2 equals P2V2T1. It's a tricky T's. Again, I read this somewhere, and I was like, I kind of like this, so I'm going to put it in. If you put the guys' names in alphabetical order, and what do I mean by that? Boyle is first, because he's B. And then Charles is next. He is C. And then Gay-Lussac is G. Remember, Boyle is your temperature guy, Charles is your pressure guy, and Gay-Lussac's are the volume guys. If you put them in alphabetical order, you can kind of treat it like a FOIL method. Boyle uses the first 2 variables, so it's P1V1 and P2V2. All right, that's Boyle's law. Charles is the second 2 variables. All right, so that's V1T2 equals V2T1. And then Gay-Lussac's is the outer and inner variables, so it's the P1T2 equals P2T1. So basically your V's go away. Okay, so whatever doesn't fit. So if you like memory tricks, maybe this will help you out. Okay. All right. And then the last slide for this lesson. If you were one of the ones that really liked the formula let me erase this. If you liked P1V1 over T1, again, I'm just going to use this whole area, equals P2V2T2, then this is the slide for you. Basically what it is all of the variables are on the points, all of the people are in between, and the way this works is the point opposite the law is the one that's held constant. So across from Boyle, temperature is held constant. Across from Gay-Lussac, volume is held constant. Across from Charles, pressure is held constant. And the way you do it is if you know Boyle's, if you need Boyle's law and temperature is held constant, well, if you're doing across the top, basically it's multiplying. So multiply your pressure times your volume. Well, if you need Charles's law, you know that pressure is held constant. So you do V, and then look what it says. Divide by T. Okay, which is what's your other laws. And finally, if you know that you need Gay-Lussac's, your volume is constant, so it's pressure divided by your temperature. So your P's divided by your T. So again, that's only if you like the other one. That's why I really like the P1V1T2 equals P2V1T2. It's your tricky T. So again, I do like that version a little bit better. All right, that is the end of session 2. What we're going to get to next is our ideal gas law, and we'll go from there. So hopefully you got a lot out of this lecture, and then we can move on with gas laws from there. Have a great day.